Ma'am, one thing, ma'am. Ma'am, the
Mm.
assignment will have portion till last class, no?
Yes, that was informed to your CRs. Didn't they tell you?
Yes, ma'am, it's okay, ma'am.
So last class, if you remember, we were dealing with amplitude modulation. So amplitude modulation, as said before, you will have a message signal, you will have a carrier signal, and the amplitude, the maximum amplitude of the carrier will be a function of the message signal. So just try to remember the amplitude modulation spectrum and the wave. So next it was AM. We know its equation, the spectrum, generation methods, the two ways in which we are modulating it. That means amplitude generation modulated generation methods. Let me just record it. I forgot. So amplitude modulation, the spectrum, equation, generation, and the detection. Similarly, DSBSC means double sideband suppressed carrier. And why we went ahead with DSBSC? Anybody remembers? So
Ma'am, to
AM, the
save
power
power.
transmit, yeah, to save power. AM in the normal standard AM, power of carrier, power of upper sideband, and power of lower sideband. These three added together to form the total power of the wave or total power required to transmit the wave. So in order, and this part, the power of carrier, this is actually a waste component. We need not spend that much on the power of carrier because as such at the reception side, this carrier is not so important for us. Our information, that is a message signal, M of T, is contained in either lower sideband or upper sideband. So either of these two sidebands, if you are able to recover, somehow you will be able to get the message signal. So removing this power of carrier power, and that was the maximum. This component is the maximum among these two. Power of carrier, whatever power upper sideband or whatever power lower sideband is having, more than that, the carrier is having the power. So we need to suppress it. I mean, it is better if we suppress it. So that is why we went ahead with the double sideband suppressed carrier modulation. That is also another type of AM. The spectrum of that, the equation, the generation, and detection. So the detection part was coherent detection, if you remember. Coherent detection means whatever is the carrier signal generated at the transmitter, the same carrier we need to get at the receiver also. Okay, are you okay? Are you with me?
Yes, ma'am. Yes, ma'am.
Okay, so so now I want to tell you one thing. This AM is AM, different types is there. One is standard AM, standard AM. That is this thing. The normal three components: upper sideband, lower sideband, carrier. So carrier, upper sideband, lower sideband. So these three forms the standard AM. Double sideband suppressed carrier. This is also a form of AM where actually only upper sideband and lower sideband is there. There is no carrier. And next is single sideband or SSB. Okay. Can you see the screen?
Yes, ma'am, we can see the
Yes, ma'am.
screen.
Okay. So whenever there is some problem, don't put in the chat window. Which I mean, if the issue requires urgent attention, don't put in the chat window because I may not be able to see it now. So in my screen, I'm seeing only this slide. So don't put in the chat window. Just unmute and speak. So and next one is there is single sideband modulation, and in this, in fact, this lower sideband and upper sideband, it both conveys almost the same information. So why going ahead with both of them? Either the upper sideband or the lower sideband. So that is what used in SSB, single sideband modulation. And next, another fourth type is vestigial sideband modulation. This is actually intermediate of DSBSC and SSB. It's a kind of compromise between uh, SSB and DSBSC. So what you can see, the standard AM, suppose the message signal is having a bandwidth of W. To transmit through standard AM, you need a bandwidth of 2W. Are you getting it? Getting the point?
Yes, ma'am.
And this is message. Message is having a bandwidth W, bandwidth of message W. To transmit it as standard AM signal, you including the carrier USB and LSB, the bandwidth is 2W. When it is transmitted as DSBSC, what is the bandwidth?
2W.
Then also 2W, but the only difference is power is different compared to AM, power is less. And to transmit as single sideband, we need only W. Only one sideband is transmitted. And as vestigial sideband, actually W plus V, a small vestige. It is neither 2W nor W. It is more than W, but it is less than 2W. So that will be the bandwidth required for VSB modulation. So these are the four things, four types in which you are, four different varieties of doing amplitude modulation. Standard AM, we covered it. DSBSC, we covered it. And next, we are going ahead with SSB, single
Ma'am,
sideband.
I actually have a question with
Hmm.
DSBSC.
Hmm.
Ma'am,
Yeah.
isn't there phase reversal in DSBSC with the modulated wave?
Yes, I mean, are you speaking about the phase reversal of the carrier? Yes.
Yeah, like you multiply. So, how do they take care of that while unmodulating it? But doesn't phase reversal like completely ruin the unmodulation part? Like you said in AM that Ka into the message signal should be less than one so that phase reversal doesn't take place. But in
Hmm.
DSBSC, phase reversal takes place. So how?
Actually, actually, it was not the phase reversal alone which was a problem for us.
Okay.
So here in AM, what the issue was?
Basically, more power and
No, 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 not
it's
not exactly. When this is this was a message signal, suppose case one. Case two. So this was my message signal.
Yeah.
Red dots is my message signal. This is my carrier.
Yeah.
See here, you experience a phase reversal
Yeah. Okay.
for the carrier. But what
Okay.
happens? Why? That was just one information for you. Okay, here carrier gets a phase reversal. That's all. But why we didn't prefer this is AM only over
Yeah.
modulated AM.
Oh yeah. This is O modulated aim. Yeah.
Okay, modulation percentage is greater than 100. Okay, here it is percentage less than, less than 100. Or in the modulation index is less than 1, M less than 1, and M this is greater than 1. Here what happens is we loses this envelope. This envelope will get lost. That was our issue. Here we can get back the envelope very clearly. Using our envelope detector, diode circuit or something, we will be able to get the envelope clearly.
Okay. Fine. So in DSBSE, it's not demodulating the envelope. You need the envelope to demodulate the signal. Is that what?
Yeah, yes. We are that is why we are going ahead with the next technique. For DSBSE, what we are following? Coherent detection.
Coherent reduction. Okay. Okay. My bad. Yeah.
It is related with the frequency. In the with respect to frequency, we are playing to recover it in the DSBSE. But whereas in AM, we are using envelope. We are just in the time domain itself. We are trying to in the signal domain itself. We are trying to get it back.
Fine, ma'am. Fine.
Hmm?
Okay.
Okay, this is
Thank you.
extra slide that will be present when I'm sharing. Okay, this is single sideband modulation. Only one sideband, either the upper or the lower sideband is present. Hello. Answer. Yes. Yes. No.
Whoever is unmuted, can you please mute?
Okay, hello.
Ma'am, could you please ask everyone to mute?
So DSBSC, we had done the coherent detection. So now we will go ahead with one more detector for DSBSC. I mean, directly that was what actually Prashant and Prabhu sir called me right now. That's why I unmuted myself. We were discussing. So he said it is better to go ahead with one more detector. So DSBSC detection method. Last class, we studied one detector, which was coherent detector or coherent detection. So coherent detection, what we did is, we have the signal S of t, we have a product modulator, low pass filter, and a local oscillator. Okay, I mean, this was just last class session, rewinding, and the output will be the message signal. And I explained why this is important, because after the product modulator and the low pass filter, the signal which is coming after the low pass filter, the signal will be half AC m of t into cos phi. This cos phi is the recovered signal. Recovered signal will have this expression. And this cos phi is the phase difference between this local oscillator and the previous thing. At the transmitter, whatever is the local oscillator, what is the phase of that, and the local oscillator here, though it is having the exact same frequency, what is the phase of that? So this is the phase difference, and this local oscillator and the carrier generator at the transmitter should be aligned such a way that this phase is 0. So then we will be getting the maximum output from the signal. So this is coherent detection, and next is Costa's loop. That is another this is for DSBSC, okay? DSBSC signal demodulation. You have the Costa's loop. So let me draw the circuit for Costa's loop. You have a product modulator, VCO, voltage controlled oscillator, another product modulator, and to both of this you are feeding the DSBSC signal, which is AC cos 2 pi FCT into M of t. So see here in the coherent detector, what was our condition? See, recovered signal is half AC m of t into cos phi. So there is a cos phi term and there is a requirement that this phi to be 0 or very less so as to maintain to get the maximum output. If it is completely phase different, that means here local oscillator and the local oscillator at the DSBSC generator, if both are completely out of phase, what will be the recovered signal output? Voltage will be 0, isn't it?
Yes, ma'am.
So in order to manage with that, you will have, I mean, in order to, so this phase is very important. The local oscillator has to be maximum in phase with the local oscillator at the generator. So in order to maintain that, this is a circuit, Costa's loop. Here it is automatically getting maintained. There is a phase discriminator. You have a product modulator, low pass filter. Here also product modulator, low pass filter. And this channel, this upper path, it is known as in phase channel. This is in phase channel or I channel. And this part is Q channel or quadrature. Quadrature channel. So these two detectors, so here you have a detector, here you have a exactly opposite detector, and these two, the output is the cos phi term here, sin phi term here. So these two align here to the phase discriminator, and this discriminates between the phase, and here you have a feedback mechanism. See, comparing, analyzing these two phases, this phase discriminator will give a feedback to the voltage control oscillator, and hence this will generate a term. Accordingly, it will adjust the phase of this carrier as well as this carrier. So basically, perfectly, we want this channel to give us zero output and this channel to give the maximum output. So this, because this is more aligned, cos term and this is sine term. So for that, you have a feedback mechanism over here. You have a phase discriminator. So this is the Costas loop for actually enhancing the capability of the coherent, normal coherent detection. So next heading, next one more heading is quadrature carrier multiplexing. Quadrature carrier multiplexing, what happens is, or this is also known as quadrature amplitude modulation, okay. QAM, this is another name for the same thing. Here, what happens is, two independent message signals, say M1T, you have M2T, two independent message signals. These should be independent message signals are modulated on the same carrier. So what is the advantage?
It saves energy while transmitting.
It saves bandwidth. Two independent messages occupy the same transmission bandwidth. So the signal equation S of t will be AC into cos 2 pi FCT. So this is the message carrier into M1t plus AC cos 2 pi FCT into M2t.
Ma'am, won't there be self-interference if both the messages are in the same bandwidth?
No. That is the advantage actually. M1T or M2T, whichever is having the maximum bandwidth, the total signal bandwidth will be twice that. The multiply S of t, the bandwidth of S of t will be 2W. Hello? Sir. Oh, here, sorry. I am speaking about quadrature carrier multiplexing. Here, one signal is phase shifted version of another. Sorry, this is wrong. This is wrong. This is wrong. S of t is M1t into AC cos 2 pi FCT plus M2t into phase shifted version of AC cos 2 pi FCT. That is AC sin 2 pi FCT. In two different phase shifted versions of carrier, we are modulating two message signals. While writing, I didn't realize it. Sorry. So the bandwidth of this signal is 2W. If W is the maximum bandwidth, whichever M1 or M2, whichever is having the maximum bandwidth, the maximum of that, twice that is the message signal bandwidth, whichever is the largest. If M1 is having a bandwidth W and M2 is having a bandwidth less than W, the bandwidth of the transmitted signal will be 2W. So the block diagram for this quadrature carrier multiplexing is M1T, here you are giving M2T. And these two outputs are mixed together. Multiplexed signal S of t. So here the expression will be S of t, how it will be product modulator M1T into M1 into AC cos 2 pi FCT plus M2 into AC sine 2 pi FCT. So this is a transmitter. And for this receiver for quadrature amplitude modulation or quadrature carrier multiplexing is the multiplexed signal S of t is coming. It's coherent detection only. You have a product modulator. Low pass filter. Here the output will be half AC into M1T, some output proportional to message signal. And here you have another product modulator. You have another low pass filter. Here will be half AC into M2T.
Ma'am, what was the previous diagram for?
That is a transmitter. This is the receiver for quadrature amplitude modulation. That means mixing two different message signals on the same carrier, phase shifted versions of same carrier. This is the receiver for quadrature amplitude modulation. This is the transmitter for QAM. See, this is quadrature carrier multiplexing or quadrature amplitude modulation. On the same carrier with the two different, phase shifted version of the same carrier, you are multiplexing two different message signals. That means within the same bandwidth 2W, you are sending same two different messages. Okay, so the technique for that, you need a block diagram for how this transmission is possible. This is the transmitter block diagram and this is the receiver block diagram.
Ma'am, in the receiver one, the cos 2 pi FCT, it means that you are taking away the carrier wave.
No, this is a local oscillator. This is a local oscillator.
So,
Generating cos 2 pi FCT.
Ma'am, why do we need to generate cos 2 pi FCT when we are receiving the signal? Like the signal which we require is half AC M1T, right?
We need to recover. Yes. Actually, what we need is M1T. This is our message signal.
Yes, ma'am. So the cos signal from the carrier in the transmitter end needs to be removed, right? The carrier cos 2 pi.
To remove it, how to remove it? How to remove it? See, here also, here this is a transmitter. Here the message signal is having so and so. See, like this. You have this multiplexed signal. How to remove it? That was the thing exactly which is happening in the coherent detection also. What happened? See here, S of t, you have an input message signal. And let me just derive the expression here. So here, what is the incoming message signal S of t? S of t is what? S of t is AC cos 2 pi FCT into M of t. This is a DSBSC modulation. Okay. So S of t is M of t into AC cos 2 pi FCT. So that is the incoming signal. So from that you need to get this M of t back. How to get it M of t back? So you are multiplying a local oscillator frequency to this input signal. How to remove it? Here what you are doing, this local oscillator is generating a frequency cos 2 pi FCT plus pi. Okay. Shall I do this mathematically?
Yes.
Yes, ma'am.
Okay. So here in this is the detector part. So this is the incoming signal. Any doubt about it? Any doubt about this? S of t is the incoming signal and the expression of the incoming signal is AC cos 2 pi FCT into M of t. This is DSBSC modulation and detection. This is the DSBSC signal. Any doubt?
No, ma'am.
So this is my incoming signal and here local oscillator is having is generating cos 2 pi FCT plus 5. So what will be here output? Say here the output O1. So what will be the expression for O1? O1. It
We'll
will
have to
be
use
S of t into, yeah, it is multiplying product modulator. What it does, it multiplies whatever is coming as the input. So S of t is the input and cos 2 pi FCT plus 5 is the local oscillator. So this O1 multiplies these two. And so let us expand this equal to S of t, what it is, AC cos 2 pi FCT into cos 2 pi FCT plus 5 into M of t. Okay, M of t into AC cos 2 pi FCT is the input, or I'll write it before, equal to, see this one, M of t into AC cos 2 pi FCT. So this is the message signal, this is the incoming signal S of t, and into cos 2 pi FCT plus 5. This is a local oscillator signal. That is a local oscillator signal. So here O1, I mentioned it as AC cos 2 pi FCT into message signal M1T, M of t into AC cos 2 pi, need not be AC, okay. Let us forget this amplitude, cos 2 pi FCT plus 5. We are not bothered about the amplitude of this, is the local oscillator signal, local oscillator generated signal, and this is the incoming signal S1T, which is the DSBSC signal. Okay, are you okay with this much? Now I am expanding it. This can be written as, are you okay with it?
Yes, ma'am.
FCT into, I am multiplying this to cos 2 pi FCT plus 5 into M of t. I made it look like this. And this expanded. How to expand it? Cos A into cos B. Cos A cos B. That expansion if I am using, and I am getting half AC cos phi M of t plus so this thing expanded. I am getting this expression.
Yes, ma'am.
Cos A plus B, cos A minus B. So applying that, this I am getting. So this I don't want. So that is why I am applying a low pass filter. Okay, this is unwanted term for me. and this is my required term. Are you getting it?
Yes, ma'am.
Yes, ma'am.
So product modulator, and this low pass filter is actually removing the 4 pi FC term, and I am getting the message signal. So here for the message signal to be maximum, this phi term should be minimum. Phi should be 0 or cos phi should be 1 or at least approximately equal to 1. So more is this phi, the more it tends to 0, the better chance of me getting a more productive output, M of t. So that is why we want coherent. So that's what the significant importance of this term coherent is, that this local oscillator, whatever the signal it is generating, should be maximum in phase with the carrier generated at the generator. Okay, are you getting it?
Yes, ma'am.
So that is why the coherence, the term was important. And what happens in this Costas loop? It is having same as this coherent detector only, but it is having a feedback mechanism to make this phi maximum 10 to 0. So if it is not 0, it will have some output at this quadrature channel also. We want output at this I channel, in phase channel only. If this quadrature channel is having some output, it means that this is out of phase, or I mean this carrier generated by this VCO is not exactly in phase with the incoming carrier. So these two we are aligning. I mean that is why we have the importance of this feedback loop. The feedback gives the input to the VCO in such a way that, and this adapts itself and sends another tunes itself to new frequency, and then see, this is the thing, and it balances automatically. So that is Costas loop. And this is quadrature carrier multiplexing. Quadrature carrier multiplexing on the orthogonally shifted two different carriers. We are same carrier out of phase, two different phase, at two different phase we are multiplexing two different message signals. So within the same bandwidth we are able to send two messages. And this is the transmitter for quadrature amplitude modulation. This is the receiver for quadrature amplitude modulation. Whoever asked me, are you clear with it right now? The purpose of this local oscillator generating a 2 pi FCT, and how the product modulator and low pass filter circuit can remove it.
Yes.
Okay.
Excuse me, ma'am.
Ah.
For the QA, this current slide receiver, here we don't account for any sort of like local phase shift. Plus phi is not there.
No. This is without feedback. So whatever is the phase shift, that will affect.
That will affect, but we are not considering it as ideal right now.
Yeah, no. Here we are just telling you that we can mix two different message signals. We can. This is possible. Mixing within the same bandwidth. Here also, to avoid the effect, again this local oscillator, we need to go ahead tuning it with respect to feedback.
Okay, thank you.
Okay. Some other mechanisms or some other circuitry will be required. So this is about DSB-SC. Now it's SSB, single sideband modulation. So either it is the upper sideband or the lower sideband. See, DSB modulation, if this is the message signal, say MF. Okay, this is frequency 0W minus W. DSB-SC spectrum will look like this. This is FC plus W, and FC minus W. This is 0. This is minus FC, this is minus FC plus W, minus FC minus W. So in SSB, how will an single sideband modulated spectrum look like? Oh, yeah, I already had made this slide. So message spectrum, this is a DSBSC spectrum. This is an SSB spectrum with upper sideband only. And this one is the SSB spectrum with lower sideband. Okay, so this is the single sideband spectrum. So we have to make the signal, or we transmit only one of the sidebands. Other than, like, unlike DSBSC. So this is a DSBSC spectrum. Okay. Are you getting it?
Yes, ma'am.
Now, how to do that? There are two techniques. One is frequency discrimination method and another is a phase discrimination method. So frequency discrimination method, to apply this, we have a condition. The first condition is that, see, you yourself can actually guess. See here. One of the techniques, just logically thinking, one of the technique is to generate SSBs. You are generating a DSBSC signal and filtering it, isn't it? Isn't it?
Yes, ma'am.
Yes.
So filter, you need to filter. Let me change the color. So to filter it from DSBSC signal, you need a filter like this. This should be the filter, isn't it? Isn't it? Or it can be, if you want the lower sideband, you need the filter to be like this. Like this, either like this or like this. Anyway, the thing is that it needs a sharp cutoff, isn't it? Somebody respond.
Yes, ma'am.
Filter needs a sharp cutoff. Is it possible?
No, ma'am, it's not practically possible.
And practically not
Ideal
possible.
filter with sharp is not practical. It's not practical. So actually this frequency discrimination method is same as, is the process is same. See, this is a frequency discrimination method. Either it can be done as single stage or two stage. So let us focus on the single stage. You have a message signal, carrier signal, product modulator. You have this signal is nothing but the DSBSC signal. Okay. In that, from that, you are getting a band pass, passing it through a band pass filter, and you are getting SSB modulated wave. Okay. Okay.
Yes, ma'am.
Same thing. So what happens? See, if so, the same issue, when you are band pass filtering, the filter characteristics need to be so sharp that it has an exact cutoff, which is impractical. So that is why these are the two conditions for generating an SSB signal using frequency discrimination method. What? One, message signal has little or no frequency content, no low frequency content. At the zero frequency, it shouldn't have any the spectrum. And next is message signal bandwidth. Higher frequency component of message signal is much lower than the carrier frequency. Of course, that is like normal technique only. So this should be an example for my message signal. Otherwise, we were explaining with message signals like this, right?
I can't hear you.
Hello? Can you hear me?
Yes, ma'am. Now
Yes, ma'am.
See, otherwise we were modulating, or whatever examples we showed, the message signal had a spectrum like this. Okay.
Yes, ma'am.
So if the message signal spectrum is like this, when it is DSBSC modulated, what happens? This will be the DSBSC signal. And to make it SSB, we need to cut off exactly this part. That means an ideal filter with a very strong cutoff frequency is required, which is impractical. Are you getting it? Hello. Can you see me? Okay. See, DSBSC modulation, you have message signal, you have carrier, you have a product modulator. Into that you are giving product of those two is the DSBSC modulation. And I am telling you one way to generate SSB, single sideband generated signal, is creating a DSBSC signal and filtering out one of the sidebands. Okay.
Yes,
Yes, ma'am.
So I was trying to explain you the problem with certain category of signals. This technique using frequency discrimination method generating SSB is not possible. Why? And what kind of message signals? Those who are low pass signals. Low pass signals means all the message content is concentrated near to the lower frequency or zero frequency. Then what happens? The message signal spectrum, as I explained, you have a spectrum, it gets shifted, DSBSC spectrum, try to remember. And from that, if you are separating one of the side bands, what happens? You cannot have that ideal filter which can do that purpose, which can serve the purpose. For example, in this case, can you see the slide?
Yes, ma'am.
So if my message signal is like this, let us try to solve it. So what will be the DSBSC spectrum? The DSBSC spectrum, how it will be DSBSC spectrum? Here I have the carrier FC. So now, can you agree on this?
Yes, ma'am.
Yeah. So here, isn't it easier to separate the one of the side bands?
Yes, ma'am.
So here, even if I have a filter like this, if my band pass filter looks like this also, I can separate out one of the side bands, be it lower sideband or upper sideband. So what is the difference between this message signal and this message signal? This message signal is not a low pass signal. It doesn't have much, have any spectral content near to the lower frequency or to the zero frequency. But this, whereas this one is a low pass signal. Okay.
Yes, ma'am.
So that is what listed out here. To apply this frequency discrimination method, the message signal M of t should satisfy two conditions. One condition, what is it? M of t has little or no frequency content near to the lower frequencies or zero frequencies. That means the spectrum M of f has holes at the zero frequency. Is that digestible? What is
Yes,
mentioned here? Everyone, anybody is having any doubt?
One more time.
One more time. Okay.
Yes, ma'am.
So this is my message signal. Suppose, see. This is case 1. This is case 1. This is case 2. I have a message signal which is having a spectrum like that. Point number 1, this is the frequency discrimination method. Frequency discrimination method. Let me just explain. I'm explaining the thing again. Okay, this is extra slide. Frequency discrimination method. For SSB generation, it says that you have a product modulator. This is a product modulator. You have a carrier. You have a message signal. And here you are getting a DSBSC signal. Any doubt about that?
No, no.
So that we are passing through a band pass filter. And this output is the SSB. Here you are getting SSB signal. So this is the technique. Frequency discrimination method for generation of SSB is this. Block diagram is this. Ends the story. Okay, that's all. Block diagram. This is a block diagram and this is the technique for generation of SSB using frequency discrimination method. End of the story. But I am telling you, to generate an SSB signal in this technique, this message signal should have, there are certain constraints on this message signal. So why those constraints came? What are those constraints? So that is, suppose the message signal, case 1, message signal is having a spectrum like this. So it extends from minus W to, 0 to W, and my DSBSC signal will be, this is FC plus W, this is FC minus W, and here it is minus FC plus W, minus FC minus W. So this is the DSBSC signal. So now how to get the SSB signal? We need to filter it. Okay. See here. So DSBSC signal, point number, this point output is shown here. Output 1. This is a spectrum of output 1. So now how to get the output 2? This output 2 should be our SSB. This is our SSB spectrum. This is FC plus W. This is minus FC. This is minus FC minus W. See here. Okay. So how to separate this into this? We need a band pass filter. Are you with me?
Yes, ma'am.
So here I need a sharp band pass with filter with a sharp cutoff. Then only I will be getting this spectrum, right? Isn't it?
Yes, ma'am.
So, but whereas if my signal spectrum is like this, say, like this. This is my message signal spectrum. It is, my message signal doesn't have any frequency components near 0. It is just from F1 to F2. It is it contains information between F1 and F2 only. If this is a spectrum, then my DSBSC spectrum, this is a DSBSC spectrum. Isn't it looking like this? Here you have FC plus F1 into FC plus F2, here FC minus. So the spectrum shifted to here. Isn't this the DSBSC spectrum? And how will be the SSB spectrum? I just want the upper sideband, suppose. Okay. Here it is possible for me to get to filter out this part using a normal filter. I mean, using a practical filter, isn't it? Are you with me, guys?
Yes, ma'am.
So that was what I was trying to say. The message signal like this, if the message signal is having a spectrum like that, using this method, I'm not telling that there is no other way. No, there are ways, but not using frequency discrimination method. Using frequency discrimination method, you will not be able to get an SSB, proper SSB spectrum. But whereas if the message signal has 0 spectral content near to the lower frequency, you have a fair chance of getting SSB spectrum. You can have a method, generate SSB signal using this block diagram or frequency discrimination method. Is it clear?
Excuse me, ma'am.
No, yeah, tell me.
Ma'am, what if we use the band elimination filter that eliminated frequencies between minus FC and FC? And we can still obtain the upper sideband, right?
But again, this band elimination filter also is not ideal, right?
Okay.
The band elimination filter, suppose here, in this one I am trying to explain you. This case, this is extra slide. So I am going to generate a band elimination filter which eliminate this such frequency. Band elimination filter, let me use some other. See, again, the band elimination filter should have extra ideal characteristic like this. It should go like this, but it will never will. It will be always like this.
Okay.
Again, the some spectral component from the other sideband will be present. Whatever is a filter used, it should have ideal characteristic or sharp characteristics.
Fine. Thank you.
Okay. So that is why this is a condition. Message signal has no frequency, no low frequency component. No low frequency content. And one example for such a message signal is a voice signal. Voice signal varies from 20 to 20K. So it is a band pass signal, not a low pass signal. And the highest frequency of the message signal is much lower than that of FC, the carrier frequency. That applies for normal any modulation technique. And about the band pass filter, in this band pass filter has two constraints. One is pass band of the filter occupies the same frequency range. Passband of the filter occupies same frequency range as the spectrum of the desired SSB modulated wave. Okay, the passband should, of course, that is just logic. The passband of the bandpass should lie at the required spectrum. Is there anything to be confused there? my band pass filter. This is the pass band. I want the upper side band. So the band pass filter, the pass band should be in the frequency range as the upper side band. Okay, that is the first condition. And next is width of the guard band of the filter is twice the lowest frequency content of the message signal. What does that mean? Width of the guard band. So here suppose this is my band pass filter. This is the guard band. The guard band of the filter, width of the guard band of the filter is twice the lowest frequency content of the message signal. So here what is the lowest frequency content is F1. So the guard band of the filter should be 2F1. What is the significance of the guard band? Can you get it? Here the minimum frequency of the signal is F1 and the low says or the conditions on the band pass filter is one is pass band should lie in the spectrum of the required upper sideband or the lower sideband. So that I think it is logical and hope you can understand it. Is it okay? Are you getting it? First point, this one. Pass band of the band pass filter occupies the same frequency range as the spectrum of the desired SSB wave. Okay.
Yes, ma'am.
So what about the next point? Width of the guard band. Width of the guard band. Can you see the pointer?
Yes, ma'am.
The width of the guard band of the filter is twice the lowest frequency. What it says. So let us say, take this as an example. What is the lowest frequency of this message signal? F1. After DSBSC modulation, what will be the difference between the two spectrums? See, just DSBSC modulation I am telling. After this, the upper sideband and the lower sideband will be separated by 2F1, twice the lowest frequency. Okay, had you noticed it?
Yes, ma'am.
So the guard band of the filter, the band pass filter, whatever is the guard band. Guard band means what? From the there will be a intermediate band, whether it is not band, stop band as well as the pass band. So that the width of that transition band should be the maximum width possible is 2F1. Anyway, after 2F1, it should have the filter should have a perfect stop band. There should not be any otherwise some part of this spectrum will also get included in this, right? So in order to avoid that, that is the second condition, 2F1. This will be the guard band of the filter should be twice the signal. Twice the minimum frequency of the message signal. Okay.
Yes, ma'am.
So these are the two constraints on band pass filter and the so now why two stage? So this is one stage single SSB modulator. This is a two stage SSB modulator. This is to actually make it to a next higher level frequency. Instead of directly modulating it to a higher frequency, we make it into two different stages. Much higher frequency, actually frequency band, which is very high frequency compared to the message signal. We do it in stages. So this is not all about SSB. Here we dealt with the spectrum of SSB. I have to get you through the ways in the mathematical equation of SSB. That we will do later as the time is approaching. See, like AM AM, the signal expression you know. SAM. You had an expression. Similarly, DSBSC signal. That also had an expression. Similarly, for SSB, what is the expression? So this part, the mathematical expression for it, we will do it in the next class. Now it's almost time for your assignment. Okay. Hello. All gone?
No, ma'am.
Today's class is not included for the assignment.
Ma'am, at what time will be the assignment?
4:30.
Okay, ma'am.
What is the exact time now? 4:25, right?
490.
Ma'am, 419.
4:19. So shall we continue the class?
Can you upload the assignment
No,
like
ma'am.
a couple of minutes prior to 4:30? Because a lot of times we only get the notification a couple of minutes later. That's what happened yesterday for our assignment.
Ma'am, there are
Okay.
network problems too, ma'am.
Let me see.